In this video, I'd like to show you a simple example of a little attack that the eavesdropper could perform on our device-independent key distribution protocol, taking advantage of the fact that she can influence not only the entangled state that Alice and Bob are using, but also the measurements that are being performed by their devices. So let's see this. So here's the setup. Eve can prepare arbitrary devices for Alice and Bob, and here's how these devices are initialized. They're initialized in a mixed 2-qubit state, 1 qubit for Alice, 1 qubit for Bob. That's a mixture. There's a parameter C here. C is between 0 and 1. Think of it as anything you want for now. And it's a mixture of phi plus, which is just a EPR pair, and phi minus, where phi minus is the state 1 by root 2, 0, 0, minus 1, 1. Right? So these are two orthogonal Bell states. That's the mixture in which the two devices are initialized. And now here are the measurements. Alice's device will perform the honest measurements, so a measurement in the computational basis if the input is a 0, and a measurement in the Hadamard basis if the input is a 1. So that's the honest measurements. But the measurements by the B device are slightly rotated. So you can see that if C is equal to 1, this is just the CHS-H strategy. If I take C equals to 1, the state is an EPR pair. Alice's measurement are the correct measurement, and Bob's measurements, C equals to 1, you get 1 by root 2 times Z plus or minus 1 by root 2 times X, and you can check that this gives you the Hadamard and the Hadamard tilde, which are the measurements that are supposed to be performed by the Bob device in an optimal strategy. But in case C is not equal to 1, C is a little bit smaller than 1, then these measurements are slightly rotated. Now that you have the state and the measurements, you can compute what is the success probability of this device in the CHS-H game, and you can verify using a simple calculation that this success probability will evaluate to a half plus, and instead of the optimum 1 by 2 root 2, what you get is 1 by 2 times root 1 plus C squared. So if C is equal to 1, you get a half plus root 2 over 2, which is 1 by 4 root 2, you get the optimum. So C equals 1, of course, because it's the optimal strategy. But if C goes away to 1, this decreases away from the optimum success probability. Okay, so we kind of have a one parameter family of strategies here, where as you change C, not only the entangled state changes, but also the measurements being performed by the Bob device change, and the success probability in CHS-H slowly decreases away from 1 as you decrease the parameter C away from 1. The question is whether it's useful at all for the eavesdropper to prepare these devices, because it seems that this is a mixed state. There's entanglement in phi plus, there's entanglement in phi minus. Does the eavesdropper really have any advantage in guessing the outputs that are produced by the devices in this strategy? You should pause the video and think about it. Can you find a strategy for the eavesdropper? Let me show you one. The idea is to rewrite this mixed state, the same mixed state, but in a slightly different form. What I can write is I can write that Rho AB is equal to, and I can write it as 1 minus C times the average of phi plus and phi minus plus C times phi plus. But now this uniform mixture of phi plus and phi minus, if you compute what it is, it's actually a pretty boring state. It's a mixture of two entangled states, but you can rewrite it as a mixture of two product states. So in fact, this is a separable state. It can be rewritten simply as a half 0, 0 plus a half 1, 1, which means that there's a purification of this density matrix in which the eavesdropper here holds also a 0 if Alice and Bob's qubits are 0, and also a 1 if Alice and Bob's qubits are 1. And then some other side information in the case where the state that they share is phi plus. It doesn't matter, I could call it 2, for instance. So I could create the state psi ABE, which would be equal to 1 minus C by 2, 0, 0 for Alice and Bob, and also 0 for Eve, plus 1 minus C by 2, and 1, 1 for Alice and Bob, and 1 for Eve, plus C phi plus for Alice and Bob, and let's say 2 for Eve. So that's the same. I should normalize my coefficients properly, but if I do it in this way, you can check that if I trace out the system E, I reproduce the density matrix that I claimed the devices were using. But now, if that's the pure state of the system, then Eve has a large advantage in guessing Alice and Bob's outputs. Remember that the outputs that we use for quantum key distribution are the ones that are obtained when Alice and Bob measure in the X basis. And suppose that Eve measures her system in the X basis, conditioned on it not being a 2. So if she sees a 2, she throws it away. If she sees a 1 or a 0, then she guesses that Alice's output is a 1 or a 0. And this is going to be the case, because if Alice measures in X, she's going to get a 0 at the same time as Eve does, and a 1 at the same time as Eve does. So for this strategy of the eavesdropper, the guessing probability is going to be at least, well, for the first part of the state in which she has certainty of getting the right outcome, we get 1 minus C. And then the second part, when Alice and Bob are in the maximally entangled state, then this is just random guessing. That's a fraction C over 2 of the mixture, so we get 1 minus C plus C over 2, which is equal to 1 minus C by 2. So if C is equal to 1, this is no good. The success probability is a half, and that's what we expect, because if C is equal to 1, the boxes are just honest boxes. Eve has no side information. But as C decreases away from 1, you can see that the guessing probability is going to increase towards an optimal guessing probability of 1 when C is equal to 0. In that case, the state is completely separable state. So you have a smooth trade-off here. You can vary this parameter C, and you can see that here we are taking advantage of the fact that we had the freedom to choose the measurements of the B device. So if you remember from week 2, we had seen a potential attack on the CHSH game which involved a state that was a mixture of the maximally entangled state and a totally mixed state. And here you could just use the honest measurements for the Alice and Bob devices, and that achieved a certain guessing probability. Here you can do the calculation and you'll see that we're doing a little bit better. So as far as we know, the attack that I presented here is the best attack that you could perform on the CHSH based guessing game.